In this video, we're going to start taking a look at how applications work with proportions. The key to setting up a proportion for an application problem is to organize the information in a way you can pull out the important data. When solving an application, we must first identify what we are comparing. And using that comparison, we will clearly label the numerator and denominator with those things we are comparing. And that will tell us exactly where to put what numbers into the proportion. For example, a man who's 65 inches tall wants to know how tall a large tree is. He notices at a certain time his shadow is 14 inches long, and he measures the shadow of the tree. It's 48 inches long. We want to find out how tall is this tree. Well, what we can do is identify what is being compared in this problem. You might notice we are comparing the height of the man or the tree. But I say just say tall, how tall the man or the tree is. And we are comparing the shadows. These are going to be our labels for the proportion. Because I put the word tall on top, that's going to be our numerators, and shadows in the denominator. Technically, we can put these in either order. The trick is once we've established one thing goes on the top, it needs to stay on the top, or the numerator, for the entire problem. For our first fraction to fill in the numbers, we want a relationship between how tall something is and how long its shadow. Both numbers need to talk about the same thing. You notice we have a 65-inch tall man with a shadow that's 14 inches long. How tall is the man? He's 65 inches. How long is the shadow? It's 14 inches. Both those numbers talk about the same man, giving his height and shadow length. The other number then, the 48 inches, we just need to decide, is that talking about how tall the thing is or how long the shadow is? We see that it's the shadow of the tree that's 48 inches long, and shadows are in the denominator, so we put them on the bottom, and our variable must go in the other location. We can quickly solve this proportion then by multiplying the diagonal 65 times 48, which is 3,120, equals 14x, and get x alone by dividing both sides by 14. And we find out x, the tree, is 222.9 inches tall. Is that really tall? Well, in feet, if we divide it by 12, it's about 18.5 feet tall. Let's try another example where we're asked to use a proportion in order to solve a problem. Here we've got a manufacturer that knows that out of every 300 parts the company ships, 18 are defective. And they're shipping 5,800 parts. How many will be defective? What we're comparing in this problem is the parts that we ship compared to the parts that are defective. So we'll set up our proportion, labeling the numerator as the ones we ship, the denominator as the defective ones. Technically, we can put those in either order as long as once we've labeled them, it stays that way for the whole problem. The first fraction compares a shipment with defectives where we know the relationship. We know that out of every 300 parts shipped, 18 are defective. 300 are shipped, 18 are defective. All talking about the same group of parts. The other number, the 5,800, those are the ones the company has shipped. So we'll put those with ship in the numerator. The other spots are x, and we just have to start solving this proportion. 300x equals 5,800 times 18, 104,400. Divide both sides by 300. And we find out x, the number of defective parts in this shipment, is probably around 348. When working with these applications, clearly labeling the numerator and denominator with what we're comparing helps us set up a proportion we can quickly solve.